Let's start this class with a quick review of some ideas from Calculus 1 that will really set the baseline for Calculus 2, because in Calculus 2, a big chunk of what we're going to do is integrate. So in the end of Calculus 1, we learn about the integral, and the indefinite integral is defined as I have right here. So the indefinite integral says that given a function, we call it capital F of x in the definition, given a function capital F of x, that is the antiderivative, any antiderivative of little f of x, meaning when you take the derivative of capital F of x, you get back little f of x. Then we define the indefinite integral. So notice, let's zoom in here. The integral symbol with respect to the differential right here, dx, with respect to x, the integral of little f of x is that antiderivative. So, we spent a lot of time in Calc 1 talking about antiderivatives and finding antiderivatives. And then we say, well, this process we're going to call finding the indefinite integral, this process of finding that antiderivative. So then we look back at all of our our basic derivative formulas, and we can create, I'm trying to get this back on the page here, we can create what we can call a table of indefinite integrals. And these are all the basic functions. I have included this for you in your Canvas course. So this is in the module, this reference page right here of table of indefinite integrals, but hopefully you're pretty comfortable with all of these coming out of Calc 1. So these are all of the basic integral formulas, ones that we want to recognize. Notice here that I have included a couple of the hyperbolics, sinh and cosh. You got a couple of your inverse trig functions. Down here, you've got your inverse sine and inverse tan formulas for the integral. And, some of the other basics, obviously exponentials, logarithmic functions, and our good old power rule right here. We got our power rule. So all of these we want to know, we want to be comfortable with. So if we're not comfortable with those yet, make some flashcards or something, get comfortable with those so that when we're finding integrals using our basic table of indefinite integrals, that we can do those quickly. So I just want to run through a couple examples, kind of get on the same page. We come across an integral that looks something like this. And the first thing I'm going to do is I'm going to scan it and I'm going to say, is this a integral that is just one of our basic integrals coming out of our table of indefinite integrals there? And it is. I see the secant tangent and I recognize, oh, right, that is coming from, right, its antiderivative would be the secant, because the derivative of the secant is secant tangent, and so forth. So kind of just going along term by term, I'm looking at all of these. There is a little bit of rewriting I would do, like on this one right here. I notice that I call this kind of the rewrite. I won't rewrite the whole problem, but I will rewrite this because I want to think of that as a power instead of a root. So I use my algebra skills here. I've got the cube root of x to the second. So kind of back a little bit of algebra review here. When we have the nth root of x to the mth, we can rewrite that as x to the m over n using my rules of exponents. And we do want to remember, all those little algebra things that help us do calculus efficiently. So we've got 5x to the, since it's the cube root of x to the second, that becomes x to the 2/3. So I'm going to rewrite it like that in order to actually take the integral or find the antiderivative. This 1 over x, I'm also recognizing that I could think of it using my exponent rules as, it's just a 1, so I'm not going to write that, minus x to the -1. But what I have to think about that's the one rule. I'm going to just scroll back here for just a second. That's the one rule, the one power that the power rule does not apply to when n is to the negative first, the integral of x to the n, because then we'd get that division by 0. So I do have to recognize that one particular one, that the integral, or the antiderivative of 1 over x, the integral, is the natural log of the absolute value of x. So I do want to recognize that. It's not, that is not actually going to be a power rule. So I won't need to rewrite that guy. And then I'm looking here and I see that constant. So I say, all right, this is all just my basic rules of integrals, my basic indefinite integrals. I can just run through this term by term and find the integral. So the integral of 5 secant x tangent x is 5 secant of x. 1 over the square root of 1 minus x squared That is the inverse sine of x. I'm going to use my power rule here. I did the little rewrite, so it's going to be 5 times. The power rule tells me to add 1 to the exponent. So when I'm adding 1 right here, I'm adding 3 over 3, so that becomes 5 thirds, and then I divide by 5 thirds, but dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to be multiplying by 3/5 right here. I already talked about that 1 over x. That's going to become the natural log of the absolute value of x, and we were subtracting. And then, of course, we have a constant, and the integral of a constant is a constant times x. And because it's an indefinite integral, we do end up with that integration constant, because going the other direction, taking the derivative would become 0. And that is my answer. There's not much to simplify here. I could rewrite just a little bit, I guess, to simplify that. Man, there's not much to simplify on this one. 3x to the 5 thirds. I am not going to rewrite that as a root. I'm going to leave it in its fractional form. And that is my answer. And I'm going through a few steps, hopefully, that are review. But if this rewriting or your comfort level with indefinite integrals isn't quite where we might want it to be at the beginning of Calc 2, make sure you do reference this table and you practice lots and lots of these. Just practice your basic integration formulas. Let's go ahead and look at just one more here, where we've got a little bit of a subtle substitution is what we're actually working with here. But I'm not gonna call this a substitution. I want to talk about this just in terms of anytime we have our x being replaced by a constant times x inside of the function. When we're finding that antiderivative, I want us to be quick. I don't want us to have to use a u substitution, which is a topic we're going to cover in a couple videos coming up this week as well. But I want us to be able to go through this quickly. So when I come across something like the sine of 2x, what I might want to think about real quick, quick little recall off to the side, recall on derivatives. Because remember, with integrals and throughout our integration techniques and integration strategies, we are going to reference back to how we took derivatives to come up with some of our integration strategies. And here's a nice example. If we think about taking the derivative of a function that has a little constant times x composed in it. So let's just grab one. Let's take e to the 7x. That is an exponential function where we have composed a 7x in for x. Instead of just x, we have 7x. And when I take the derivative, I have to apply chain rule. Chain rule says take the derivative of the outer function, which is just e to the 7x, and then multiply by the derivative of the inner function, which is 7. So when we're taking the derivative, notice right here, I'll highlight it. Notice we multiply by that constant. And so in a similar way, when I take this derivative, let's go back to red. When I take this derivative, I'm going to get the derivative, capital F prime of k times x times k, which, by the way, we did talk about how we could also just call that little f of k times x times k. So we've got that constant. When we take a derivative, we're multiplying by that constant through the chain rule. Now, when we multiply by that constant through that chain rule, if we want to go the opposite direction and we want to integrate, find the antiderivative, what we're going to do is, instead of multiplying, we do the opposite because we're finding the antiderivative. So notice right here in the formula, when we're integrating little f of k times x, we find its antiderivative, capital F, evaluated at kx, and we multiply by 1 over k, or divide by k. So the opposite of multiplying by k would be to multiply by 1 over k, or divide by k. It's saying the same thing. So the reason I bring that up is because we're going to see that so often, we want to get comfortable with it. We want to be efficient with our integration techniques. So notice right here, I see the 2x and I see the 5x in a integral of the sine of 2x and an integral of e to the 5x. So what we're going to do is we're going to find the integral of the sine of 2x to start with. So let me change from my highlighter. So the integral of the sine of x would be negative cosine. So we're going to get negative cosine of 2x, and then because we're finding the antiderivative, the integral, we're going to divide by 2. Now you can always check your work, right? If you wanted to go back the other direction, think about taking the derivative. If you took the derivative of this integral, would you get sine of 2x? And you would, because the derivative of negative cosine is negative sine, so positive sine of 2x, and then you'd have to multiply by 2, and that would cancel. And so this formula will work for any composition that is simply kx. So then when we take the integral of e to the 5x, so we already have the minus, e to the 5x, the integral of an exponential is itself, so we get e to the 5x, natural exponential, and then we divide by 5. Now this is an indefinite integral, so we will also have the integration constant plus c. Now I would look to see if there's anything I can simplify. There is nothing to simplify here. I am not going to rewrite it. I'm going to box my answer, and there we go. Okay. So anytime we see something of this form, we do want to just be quick with it and be able to evaluate that, that simple substitution from x to kx. We want to be able to quickly evaluate that and adjust when we're taking the integral with a 1 over k. Okay, so definitely practice with these, get some work on these, and we'll talk about definite integrals in the next video.